are ready to kick things off. Right, nice. We are ready to get started. So, whenever you guys are ready as well, we can kick off.
Yeah, let's kick off. First of all, welcome back to the public deep dive. And this time around, I'm going to invite our fantastic developer, Gita, to be on stage and showcase the technical achievement we have done together to really allow the community user to use their OpenSea accounts as a social tools to verify the wallet. It's much more than what I had expected, but Gita spent so much efforts to get job done. Kudos to him, and I'm going to give the floor to Gita to, and he will give you a fantastic, walkthrough here today.
Thank you, Raymond. So let's get started. It's good to be back again with another session. So, can you just let me know if you can see my screen?
It's coming through for me.
Okay. So, hello everyone. So today in the Dev Deep Dive, we'll be taking a look over the new feature which Collab.Land has introduced, which is the OpenSea Marketplace Auth, and it will be more of a technical overview. And let's get started. So, the agenda for the presentation is first to talk about what exactly Marketplace Auth means, and next, then we'll talk about why start with supporting OpenSea Marketplace Auth. And after that, we'll also discuss some of the technical hurdles which we had to overcome to actually support this while keeping the entire system trustworthy as well as transparent without violating any of the terms of services of any of the vendors which we use. And one of the ways which we actually do that is then we'll give you a small overview of the verification process. And the verification process actually uses a technology or a algorithm called image steganography. So I'll give a small introduction what is image steganography, and after that I'll take a technical dive into the verification logic, and through flowcharts I'll explain the entire thing. And then we'll also see a bit of the code which goes into this entire logic, and then I'll conclude the entire presentation. And heads up, in the last dev deep dives, we had a lot of discussion about loopback, and that will be really important here. So if you remember whatever Raymond has taught in the last dev deep dives, you'll actually understand a lot about how the extension point strategy and how loopback actually helps us to write an extensible code, especially for complicated logics like this. So what is Marketplace Auth? So Marketplace Auth is the next wave of authentication strategies in Web3. It's like a mode of authentication where the user verifies their identity through a marketplace profile which they have already created, and through a marketplace vendor which they already trust and use for everyday NFT transactions and trading. And we understand that Web3 should be accessible and easy to adopt for new users. Marketplace authentication actually allows users to safely authenticate their identity without signing signatures with like on every website they want to authenticate themselves. So there's this single source of truth. Like you trust OpenSea and everyone trusts OpenSea. You're already doing transactions on that, and you sign a signature on OpenSea and you create your profile. And OpenSea knows that, okay, this profile has this wallet address linked to it. Then what Marketplace Auth does is basically use that source of truth which OpenSea has verified, and then use that to actually verify your identity. And you do not require to sign on every website or every page. So what is why should we support OpenSea Marketplace Auth? So OpenSea is the world's first and largest digital marketplace for NFTs and crypto collectibles. It actually allows users to create profiles using their wallets and then customize their profile pictures, bios, social media handles, and basically it's like, if I would give a comparison, it's like any social media platform. It also shows the NFTs you have collected and the NFTs you own and all that. So OpenSea actually allows developers to access their API and then also get access to collect user profiles and the wallet addresses which they are verified with on OpenSea. So whatever user you are verified with. So suppose if my username is ABC123, OpenSea has a wallet address which they've already verified with you or with me in this case, and they link that to that profile or that username. So once the user verifies their wallet on OpenSea by signing signatures, developers can then actually use that as a source of truth to authenticate users directly without them again initiating one more signing message and then taking that signature and then verifying it again. So they can trust OpenSea and basically channel that trust towards Collab.Land as well. So why there were technical hurdles? This is one of the one of the very famous personnel, Mahatma Gandhi, and one of the favorite quotes I would say I have. That is, he says that it's difficult but not impossible to conduct strictly honest business. And at Collabland, trust and transparency is something which we put to utmost priority. There is absolutely no question involved if there's never any compromise on trust and transparency. And although we have seen certain implementations throughout the internet which use web scraping to actually do OpenSea verification via the bio, the OpenSea user bio. But that actually, when we went through the terms of service, that actually violates the terms of service of OpenSea. And that is why we wanted to use whatever available resources we had from the OpenSea API. And we wanted to be transparent both with OpenSea and you, the users of Collab.Land. And we figured out that OpenSea API does give us access to the user profile picture as well as the wallet address because that is already verified. And that is where this entire idea started forming or it started to begin. So just to give an overview of the verification process, the OpenSea Marketplace Auth has a verification process where the user goes through a certain number of steps. So initially what you do, you go to the Let's Go button and I wanted to show the demo here as well, but you'll find the demo in all our socials and there's also blogs which you have written. So I'll just keep it on the technical side more because then I might be time constrained. So I'll just tell it in text as of now, the entire verification process. So what the user does is they click on the Let's Go button and now they want to add a new wallet. They add a new wallet and then they're redirected to the wallet connection page. And on the wallet connection page, now there's this new button or new wallet option, you can say. It's named as OpenSea with the OpenSea logo. So when you click that, you actually get prompted to give your OpenSea username or the wallet address which you have linked. Anything works, either your OpenSea username or the wallet address which you have linked. And what our API does is it returns you an enhanced image. And I'll get more into the depth of how this enhanced image works and how we create it. But once you get that enhanced image, you're prompted to actually download that enhanced image. So you can download that enhanced image, and then what you can do is you can upload that Collab.Land enhanced image to your OpenSea profile picture. And what you can do once you have uploaded it, you can come back to the wallet connection page and then you can click on a button called verify. So there's two steps. One is you generate an image, enhanced image, by putting your wallet. Three steps. My bad. So first is you generate an image by putting your wallet address or OpenSea username. Second is you download it and upload it to your OpenSea profile. And third step is to verify it by clicking the verify button. So once you do that, we detect your new profile picture, the Collab.Land enhanced profile picture, and then we verify your wallet address. And if it's verified, if it's okay to go from our APIs, we add that wallet connection. So you can see there's no signature verification or there's no message signing involved here. It happens entirely through this single source of truth, which is the OpenSea marketplace. and it's easier to onboard users who already have a hobby of collecting NFTs, and they've already verified themselves on OpenSea. So we can use that, we can channel that source of truth into Collab.Land API. So one of the technologies which we use in doing this entire thing is image steganography. So there's a huge definition that it is a practice of concealing information within another message or physical object. So here you can say it's a digital message or a digital data, which is your image. And steganography can be basically used to hide anything. It could be text. In our case, it's a verification code. You could hide images within images, video within images. You can hide anything which has bits and bytes. And the image which you hide in is called as a carrier image. So that is basically your profile picture in this case. And the data which we conceal is the verification code. It's like a one-time password, you can say, if I explain it very simply. So Collab.Land actually uses image steganography for a very specific reason. We do understand, when you have a profile picture, it's very personal to you. It's very adored by you. And that is something which you do not want to visually modify, or you do not want to, depersonalize the entire thing. So we wanted to keep it as less intrusive as possible, our verification method. So image steganography actually allows that. So when you get the enhanced image, you'll actually see it's not that visually different from your original image. For static images like simple PNGs or JPEGs, which do not have any moving images within them, there's absolutely no difference. So you're confident enough to upload it so that it doesn't appeal visually different. For GIFs, there's a slight change in the image which is almost unnoticeable, but that is a technical constraint which we have, and that is very minimal. It's almost unnoticeable to the point if you blink, you'll miss the change. So image steganography actually allows us to minimize this visual change, and that is how we actually keep the visual construct of the image almost similar or entirely similar while changing the data behind it and basically concealing our verification code or the one-time password, if I would say. So now let's take a small technical dive into how this entire thing works. So there are three entities, as you can see. It's one, you, the user. Second is the Collab.Land API, and third is the OpenSea API. So what you do is, as I said, the first step is you send your OpenSea username or the wallet address which you've linked to OpenSea. Collab.Land API actually takes that, and then it fetches the profile picture from the OpenSea API, and that is something the OpenSea API gives. Once it fetches the profile picture, the OpenSea Auth service is put into gears. This service, this loopback service, is responsible for generating enhanced images as well as verifying the enhanced images once you're done with step number 1 and 2, when you're clicking verify in step number 3. So what does this OpenSea Auth service do? It actually does pretty simple things. Now that I put it into you know perspective, it actually does pretty simple things. So first is we compute a image hash. Now, why is this image hash computed? So this image hash is computed just to keep a check on whether you have actually uploaded a new picture or not. Sometimes it might happen that you have uploaded a picture and OpenSea API takes a bit of time to actually reflect it on the API. So in that case, the front end actually tells you, or our website actually tells you that please wait for some time if this error is coming, or just check if you have uploaded it or not, if it's reflecting on your OpenSea profile or not. So the image hash is something which we can check. So as soon as so the image hash is something. It's very interesting. As soon as you change the data behind an image, even though like the physical or the construct of the image, the visual construct of the image is same. If you change the data behind an image file, the hash changes drastically. And that is how you can actually check that the image has changed or not. Once we compute the image hash of your original profile picture, we create a temporary magic code, is what we call it, or you can call it a one-time password. It's basically the verification code. And then we send your original picture and the magic code to an image parser service. And this is where the previous session's look back knowledge kicks in. So the image parser service is supposed to first inject the magic code via image steganography to your image and then return the enhanced image. Second, it's also responsible for taking the enhanced image and then extracting the verification code and then matching the verification code. So in the first case, when you're creating an enhanced image, what the image parser service does is it determines the MIME type of the image. So any type of image which you see on the internet has something called a MIME type. You can call it as a classifier of the image. So JPEG images, PNG images, SVG images. How does one know that these three images are of different formats? The way they know, the way us servers or in general computers know is through the MIME type. The MIME type actually determines for a computer, it determines what type of an image you are uploading or downloading. So the MIME type, suppose for GIFs, is image slash GIF. For SVGs, it's image slash SVG plus XML. So different images have different MIME types, and that is actually how we understand which parser or which verifier we have to call. And how do we actually inject these multiple image parsers and verifiers into one single point of entry? That is where extension points come into place. So after determining the MIME type of the image, and already the image parser service has the magic code as well as the original picture, what we do is we send all this data to the extension point. This extension point then determines which parser which has to be called. And that is why you can see what happens next is there's this branched flow, because all of these parsers are linked through the extension point. It's the job of the extension point to take the MIME type and then determine which parser it has to call. Once it calls the parser, the appropriate parser, that parser's job is to parse the image, inject the magic code into that image, and then return the enhanced image. Once the OpenSea Auth service gets the enhanced image, it then gives it back or throws it back to the front end, which is then displayed on the front end. And moving on to step two, you download that. Once you download that image, then your job, the user's job, is to upload it to the OpenSea profile picture. Once you've uploaded to your profile picture, that is step two, done. Then, as I said before, step three is to click on the verify button. And once you click on the verify button, this is the second iteration of the OpenSea Auth service. Now you can see what is the second job of the OpenSea Auth service. So once you click on the verify button, it again comes back to the OpenSea Auth service. It starts working. And the first thing is to fetch the profile picture. And as soon as it gets it back from the OpenSea API, it computes the image hash. Only when the image hash has changed, it will know that, okay, the user has updated their profile picture and there's a new profile picture available. Because there's no point in checking the same profile picture, right, which is not enhanced. And sometimes, as I said, OpenSea does take a bit of time sometimes to actually update their API or their database records or whatever infrastructure they have on the backend that to get updated. It might take some time. So there's this, I would say, safe check or a fail safe, you can say. If the image hash is different, we are sure that the user has updated the profile picture and probably with the correct, Collab.Land enhanced profile picture. And we're good to go. So then we say, okay, let's start processing the other parts of the flow. So if the user has updated the profile picture, what we'll do is we'll then get the magic code from our internal records. We'll get the magic code for that user, which we had generated. And since it's like a one-time password, you may say, it also has an expiry. So what we recommend is finishing it within 5-10 minutes at max, like the entire verification flow. So we get that from an internal records, and then we send this enhanced image and our internal record, which has the magic code, to the image parser service. And again, you can see the image parser service does the same thing. What it does is it determines the MIME type of the image, and then based on the extension point, it passes it to the parsers. And now what these parser classes do is the second function. So I'll actually come to I'll also show another diagram which actually explains how each parser does. So the second function of these parsers is to take the internal record of the magic code and the enhanced image and then try to extract the magic code from those enhanced image. So it might be a case where someone is just trying to break the system and they upload some other picture which does not have any enhancement done by Collab.Land. So if it fails, then we output in the we output in the front end that we fail to verify, because if there's no magic code in your picture, or it's not the Collab.Land enhanced picture, and if it doesn't match, we won't verify your wallet connection. I think that's understood why we do that. It's because of security. So it tries to extract, as I said, it tries to retrieve the magic code from the enhanced image, and then it compares. So there's actually two types of comparisons going on, which I'll also tell, 5-10 minutes from now on. We have a very simple text-based comparison for certain MIME types. We also have a custom machine learning algorithm, which is written by the team, which actually compares it on a term frequency cosine basis. So it's not a simple cosine similarity running. It has custom tokenization with vectorization, and then we use a term frequency from those vectors to actually compare the similarity between the two codes. So there's two ways of comparing the magic code. But if we get a thumbs up from our API or the logic which we have written, uh, definitely for machine learning algorithms, we do not have a 0-1 thing. We have a tested parameter, a certain extent to which we'll agree that okay, these codes are similar, and we've extensively tested it. Based on that code matching, then we'll return a success or error. And if you get a success, your wallet is linked. Congratulations on not signing any message and linking your wallet. So now coming to the heart and the brain of this entire flow, which is the different image processors or the image parsers, as we call it. So we have classified, actually, in order to write this entire logic, we have classified images, any type of images, be it SVG, PNG, JPEG, uh, and others. We have classified into two types. One is a dynamic image, as we call it, and second is a static image. So a dynamic image could be a animated WebP image. So anything which has animations in them, and any image which does not have animations is a static image. So there's mainly two types of logics, and a bit of image manipulation here and there. So let me just talk about how we process GIFs, and second is how we process SVGs. So for GIFs, as I said before, there are two types of work these parsers do. One is parsing the, basically injecting the magic code into the GIF, and second is verification. So for parsing, what is the inputs? We have the magic code and the original profile picture. What we do is we create an image with the GIF dimension. So each GIF has these multiple frames within it. It's like a movie, right? So you have multiple frames and you have delay between these frames. So what we do is we replicate or we create an image with the magic code, and it is of the same dimensions of any other frame which is available in the GIF. And then what we do is we inject this in the GIF. So there's basically we're modifying the GIF slightly, and we put very less delay, like the least delay you can put. So whenever the enhanced image, if you look at the enhanced image, there's this brief flash of the magic code, and then it's not visible, and it's totally at the bottom. So as you might have noticed, OpenSea actually puts a circular mask over your profile picture. It's not even visible in that circular mask. It's that small. So there's this brief flash, which is the frame injected inside the inside the GIF image, and that is how we enhance the GIF image and we send it forward. Once you've uploaded that, we actually get that enhanced image from OpenSea, and then we extract that magic frame code. And now what I have is an image which has a code written in it. And the industry standard way of detecting text within an image is OCR, which is optical character recognition. It is also a machine learning algorithm which works. We use a OCR service provider to detect the text. And once you've actually detected the text, so due to compression, so whenever you are dealing with images, you actually have to keep compression in mind, image compression, because OpenSea is not dealing with tens or thousands of user data. It's dealing with probably millions of users' data. And it does not have so much storage space to store everything in high quality. It has to apply some kind of compression algorithms to minimize the file size before it can upload it to its records and then later reflect it to their API. So in order to compensate for that, once we get the text which we have OCR'd, actually there's sometimes, and what I have noticed from personal experience, majority of the times you do not get all the characters recognized. So then, if you have this partial of the magic code, and if you have the magic code from the internal data, how do you actually check if both of these are similar? And you have to also keep in mind the way OCR actually detects and the way it tries to detect these tokens or these characters. So we tried using various off-the-shelf cosine similarity algorithms, but we actually didn't get consistent results, I would say. And later we sorted to creating our own custom machine learning algorithm, which actually uses term frequency and custom tokenization and vectorization to achieve a similarity. And after we have achieved the similarity, then we actually check the similarity percentage based on the parameters which we have done after testing, which we have set after testing. And that parameters allows us to decide if we can pass this as a code similar or deny that no, it's not similar. It does not pass through our guidelines. And based on pass or fail or pass or rejection, that is returned back to the user. For SVG images, it's actually a bit simpler because for SVG images, SVG themselves are XML files. So XML file is this markup language. So XML is extended markup language, which is basically text. So it's easier to actually create a custom XML element and then inject it into the SVG image. And in this case, SVG also gives us the flexibility to entirely hide that magic code. So if you're dealing with static images, there is a high chance that the enhanced image which you get, you cannot understand the difference. And we have tried our best to conceal and not modify your profile picture visually, in order to protect the personalization which you do. So for SVG images, you'll actually not find any difference. And you can easily, happily upload it to your OpenSea profile picture. Verification itself is also very easy because since, as I said, it's an XML document, technically it's an XML document, you can just try and detect for that XML element. And if it's there, we verify it. We verify the magic code. Obviously, we match the magic code with our internal records before verifying. That goes without saying. For PNG images and also for JPEG images, we have a SVG containerization algorithm. So basically, we containerize the static image into an SVG container, and then we run the SVG parsing logic. Similarly, we extract the magic code from the containerized PNG, which is like basically an SVG verification logic, and then we check the magic code for equality. Also, one of the things which I should have included in this is WebP. WebP actually is a very tricky file format. So WebP actually allows you to store both static images as well as dynamic images in the same file format under the same MIME type. And we've applied some clever logic to actually detect. So you can actually try and detect the number of frames in that WebP. So if it's a single frame WebP, that's basically a static image. And if it has more than one frame, that's a dynamic image. and that is how we process the WebP. So this is the entire flow chart of how this works. It might seem a bit overwhelming at first to understand, but we have tried our best to actually minimize the user steps, and we have boiled down to 3 steps for the users. So just to reiterate, step one is to actually input your OpenSea username or your verified wallet address in that model. Once you get the enhanced image, step two is to download that enhanced image and upload it to OpenSea. And then step three is to click the verify button on the wallet connection page. And that completes the entire flow of your verification. Although all this complicated logic works under the hood, but for the users, it's pretty simple and there's no complicated message signing as such. So, moving on. So, let's see how the code looks and let's get a bit more technical into this. So, the entry points of the OpenSea APIs, there are two entry points. One is the image generation logic, and second is the image verification logic, which we usually call the callback API. So if we go to the image generation logic, you can see as soon as we get the profile picture, what we do is we create the magic code, and all of this happens inside the OpenSea auth service. So in the get profile picture logic, you can see that we send request to the OpenSea API and we get the profile details. In the profile details, we get the wallet address which you have linked, and that is how we actually can store the wallet address. And then later, once you're verified, we insert that into our records. And next step is to actually get the profile picture. So the profile picture is also one more OpenSea API route which we use. And once you've gotten that profile picture, what we do is we create the hash or we compute the image hash. We use the MD5 hashing algorithm to actually compute the MD5 hash. And then what we do is we create the magic code. The magic code is just a simple alphanumeric code, and what we do is we store your magic code, wallet address, and your original MD5 hash, if I can show. So we store your magic code, wallet address, and MD5 hash for a temporary time in our Redis database. Because, as I said, it's a one-time password. We won't store it for the entire duration, and we want it to expire. So once we've stored this, we return something called a sign-in state. It's a small slug which we use to actually just keep a track. So if you have ever seen like different payment integrations, there is something called session IDs. So you can consider a sign-in state to be something similar sorts of a session ID. It's like a code abstraction on top of it. So we do not want to pass the raw hashes and all that to the front end. We just pass a simple session ID or a sign-in state that when you give a callback, just pass me the state and then I can verify everything from there. Like I can get all the data from that. So once you've computed the MD5 hash, we have created the magic code, we've got the sign-in state, then we pass this entire details to the original image, the MIME type, and the magic code to the image parser service. So now let's open this image parser service. This is an entire work of art. So what we do is, this is an extension point, and you can see by seeing this decorator. This decorator actually tells that this image parser service is an extension point. And what does this image parser service do? So this actually has two functions. One is the parse image and the verify image. As I mentioned, there's a parsing logic and there's a verification logic. And this is where the extension point starts to play. You can see that this code line, right? Const parse equals to this image parser dot find. This line actually determines which parser has to be called. And how do you get the array of parsers which are, pointing towards this extension point? That is by calling this decorator on a image property, which is the extensions.list. That actually allows us to list all the extensions to this extension point, and we fetch the extensions based on the MIME type, as I had discussed earlier. And here you can actually see all the parsers which we support. So we support GIFs, JPEGs, PNGs, SVGs, and WebPs. That actually covers majority of the file formats which OpenSea uses for profile pictures. So if I just open any one, right? Let's just open any one. Suppose a GIF. You can see for decorating this class, this GIF image parser class, one, I've mentioned the MIME type, like which image is supposed to come to this class functions and get processed. Basically, how which image is supposed to be processed by this class. And second is you can see I have also mentioned the extension for. So this extension for actually allows us to create, this extension for that extension point. So this line actually tells loopback that okay, this GIF image parser class is an extension for the image parser service, which is an extension point. And then it has two functions, parse image and verify image. So coming back to the image processor, image parser service, sorry. Uh, so what you can see, then what it does is it takes the parser, it parses the image, and then it returns it to the front end. And then the front end returns the sign-in state and the enhanced image back to the user. So the backend returns it back to the front end, basically the user. The sign-in state is something which we store it in our React context because it's nothing to be used by the user. It's like an internal thing. And the modified image is what gets displayed, and you can then download it and upload it. Once I've uploaded, and once you click the verify button, this is the second controller, which actually is the entry point of that callback function or the verification function. And what we do is first we extract the sign-in state. As I said, a lot of data is abstracted from the front end by the sign-in state, and we take that sign-in state from the request. And what we do is we check for sign-in expiry. So if you've ever paid on a payment service, you've seen that every payment which you do has this certain expiry limit. Like you have to complete this payment within 15 minutes, something like that. So if it is expired, we do not keep that data because it's all of it is temporary data. So we check for that expiry, and if it's not expired, we get that CE details, which we had stored, which is the original magic code which is required, like the internal record of the magic code, the original MD5 hash of the image, and the wallet address against which this record has to be created. So now what we do is we get the profile picture. So there's two steps to getting the profile picture, as we have seen above. First is to get the profile via the wallet address. We get your profile, and then using your profile, we get your profile picture. So once you have gotten your profile picture, what we do is here you can see there's this function which actually takes the original MD5, takes the enhanced picture, computes this MD5 hash, and if it matches, it means that either OpenSea is taking some time to update it on their end, or the user might have forgotten to upload it. So we throw a small error which notifies the user that please check if you have uploaded, and if you have uploaded, then please wait a few minutes for OpenSea to update its records. Once all of these rudimentary checks are done, rudimentary but essential checks, what we do is we start creating the wallet connection, and then we save your wallet connection. So this is the entire code flow. Now coming to the parser services, because that is the most interesting part. So let's talk about how GIFs work, because I think from what I explained, uh, SVGs is pretty simple, because for SVGs what we do is we just simply call a function which just injects that XML element into the SVG XML, and you get back the data. So let's see the parse GIF image function, because it's really interesting. This is how GIF parsing works. So what it does, as I said, the first thing is to actually create the magic code frame. And that magic code frame is created of the same height and width of any of the GIF frames. And this is usually done through, let me just open this function. You can actually see this is usually done through very popular image libraries like Sharp and Gim. We have a combination of them. And once this frame is created, what we do is we encode this into and inject this into the GIF. And then we return back the data. This is an this is the easier part, I would say. Now let's go to the GIF verify image because this is where it gets really interesting. So for the verification image, what we do is first we extract the magic code image, and then we use our service. So we use AWS extract to actually get OCR, and we detect the word from the image. Once we have detected the word from the image, and whatever OCR, whatever extract has returned, we take that and then we pass it to this verify magic code similarity function. This verify magic code similarity function actually calculates the TF cosine similarity, as well as it also calculates the Levenstein distance or the Levenstein similarity. So you might ask, why didn't I talk about Levenstein distance? Because Levenstein distance is like a control, I would say, for us. So in order to keep the range of value similarity values to a certain mediation, to moderate that entire thing, we use a combination of TF cosine, which is a term frequency and cosine similarity, and the Levenstein similarity. And we have these weights. So it's like a weighted mean between these two similarities, which actually outputs the final similarity, and then we verify it. So Levenstein similarity is pretty easy to calculate. There are many off-the-shelf libraries which you can use. But TF cosine similarity is where things become very complicated, I think. So in order to calculate the TF cosine similarity, we actually have vectorizer functions which use n-grams. So I think from here on, I'll take very short amount. I'll take 5 minutes just to explain what I'm doing. Anyone who has a background in machine learning, I think, will enjoy these next 5 minutes. So what we do is we divide the entire strings into tokens, and we have our own tokenizer functions. Once we get the tokens and we have the tokens of both the strings which we have to compare similarity to, we create a bag of words. This is also called an n-gram strategy. So we use n-grams to then create TF vectors. So TF vectors aren't your usual normal, vectorization of n-grams. What it does is it also applies something called term frequency into this vectorization algorithm. And after that, after creating the TF vectors or the term frequency vectors, we calculate the cosine similarity between these two. And that is again passed back to the original function, which then takes the Levenstein similarity, matches it, normalizes the entire data, and then compares it against a set standard which we have. And that is how we check if your wallet address is verified or not. In the case of dynamic images, in the case of static images like SVG, it's pretty simple, as I said, because mostly it's mostly I would say a text match, but it's like an XML element match. So for this, it's really easy. We just take your, so you can see actually. So we take this parse image function, and what we do is we just inject it. So if I can come back to this helper function, you can see that we are creating an SVG. We're first creating a SVG canvas. We're putting your SVG image, and then we're just creating our own text element which has your code, and then we're just returning the final SVG. And for verifying SVG, it's way easier. So what we do is we just put a regex, we just put a regex verification on your SVG, and we see if our magic code exists or not. So that's all. So SVGs are pretty easy to do, but for dynamic images, it's a roller coaster, I would say. So coming back, so now let's conclude the presentation. I'm sorry, it was a huge presentation, but I wanted to cover everything. So the OpenSea Marketplace Auth actually opens up a new avenue of research into different marketplace authentication systems. It's a first of its kind, and as James also talks in the AI research meetup, we always are researching into new mechanisms, new authentication mechanism, new different mechanisms, and integrate them AI, ML, and all that. So OpenSea Marketplace is where you can see an example of how we created our own custom machine learning algorithm to actually incorporate this entire thing and get it to work. So marketplace authentication systems will also help users maintain a single source of truth. So you can create a profile on OpenSea, and that itself serves as a single source of truth for everything else. It's If you think, it's somewhat like Google OAuth. So you have a Google account, right? And then you log into different websites using Google, but you've created an account only on Google, right? So you've signed a message on OpenSea, and that is how OpenSea knows that that wallet belongs to you. And these marketplace authentication systems, or these OpenSea marketplace this actually allows you to keep a single source of truth, which is OpenSea, and then you can use different service providers like Collab.Land who call their API and then verify your wallet without even you needing to sign any message. So that's all. Thank you for listening. I hope you guys enjoyed, and I hope to see you guys soon again. Keep exploring, keep building. Thank you.
So thank you so much, Gita, for the fantastic walkthrough, and there are a lot of technical details. Could be a little bit overwhelming, but hopefully it shows the passion we have here to solve the pain points each of us potentially run into. And my wish is for the marketplace providers to come up with some simpler and standard way to allow the users to take control of their knowledge and share the knowledge meaningfully across multiple decentralized apps. So that's my finger crossed. Thanks.
Thank you so much, Kira. I really love when more members of the team come to present, and so that everyone gets to know them as well. And you do a fantastic job with your presentations. It was a lot of information, but I do always find them super interesting. So thank you so much for joining today.
Thank you. Thank you, everyone.
All right, let's also mention, if anyone has any questions, please feel free to drop them in the stage chat. Also, in the Dev General, we always take a look at those. Or you can also raise your hand in any of these presentations if you have any questions and would like to be brought up in the stage. I see a question from Nerd in the chat for Gita. What's the sigma size for the comparisons?
So currently the parameters are so when we're calculating the weighted mean, we actually have a 0.65 to 0.85 ratio of the Levenstein and the TF cosine similarity. And in order to cut that off, based on testing, we've gotten a 45% similarity. So if there's more than 45% similarity, we're considering it as a go. And if there's less, we are just rejecting that. And most of these parameters may change throughout time, and that is where we, depend on a lot of feedback, because definitely, any machine learning algorithm requires a lot of data to actually compute this. And since we've created our own, you can say that all the data which was there is basically to test like what we have tested. So, if ever you have done testing, and you are very confident that you have uploaded the correct picture, and you do not find similarity, or you get rejected by the API, do reach out to the support team. We'll be more than happy to actually look at your case and then solve it. Maybe. But we have tested our best, and 45% is the bar, I would say. Yeah.
Hey, thanks for everything, Geeta. Really appreciate the in-depth explanation of everything that you went through here. Um, This is sort of unrelated, but have you heard of Glaze before? It's basically NFT. How do I say this? AI protection for artists, basically, which uses a lot of the same kind of ideas of what you've talked about here, with like adding metadata presentations and really digging deep into thinking about how machine learning works.
So actually, the entire development of this has gone through a lot of curves and turns. I would be more than I would be more than happy to actually list out the entire research process for this, because so as I said, compression is something we had to take care of, and we've actually also in the past applied a lot of complex image steganography, but all that used to get lost when compression takes place. So whenever we are doing any image steganography, usually compression is something which is not taken in hypothetical situations, but in practicality, compression enables us, or I would say it allows us to take some very hard decisions. So I actually tried a lot of here and there before actually coming to the final algorithm. But yeah, as I said, if people are interested, I'm more than happy to actually list out and basically walk everyone through the road which we had taken for OpenSea, because it's been a long road. That's all I can say.
Sounds like this would be a really cool dev blog post.
Definitely, definitely.
I think, guys, it may be time now to distribute our POAP. What do you guys think?
Yeah, let's do it.
Let's go. I'm ready if you are. So, you guys, for everyone in the audience, if you would like to claim today's deep dives POAP, let's get to it. We're using the POAP mini app as usual, but in case that you are not familiar with it, it's all with the slash command here in the Discord. You can use the state chat or the general chat, should work in any of those. And the command would be slash POAP claim. It will ask you for a claim phrase, and in that little square, you will write down OpenSea, all lowercase with no spaces in between. OpenSea is the secret word to claim the POAP. Again, that's with slash POAP claim. And then in the claim phrase section, you write OpenSea. That would be OPENSEA. OpenSea. Once you write it down, hit enter and you'll receive a code to claim your POAP. A secret topic already claimed his. Thanks for letting us know. And also, if you have any issues claiming the POAP, you can let us know. We'll help you troubleshoot, or otherwise, I'll get you a code to claim your POAP. No worries about that. I'm claiming mine right now.
I love how there's a C in the poem.
Yay! I'm trying to play a little bit with that, with the backgrounds and adding some stuff to them. So I'm really glad you mentioned it. I hope that everyone likes it. Right, we have 10 collectors already. But just in case that anyone missed it, Once more, in order to claim the POAP, all you have to do is write slash POAP claim, and I'll also send the command in the chat because that's always easy. You can click the message I just sent in the state chat saying POAP claim. If you click it, it should work for you, and you just need to write down the claim phrase. That would be OpenSea. All lowercase with no spaces in between. OpenSea. Oh, I see that Anita claimed as well. Thank you so much, Anita. Really love to see you guys in all of our events. Really appreciate it. All right, I think that we are ready to wrap things up. What do you guys think?
Yeah, let's do it.
All right. Thank you so much, Kira, and thank you, Raymond. Just in case that you guys in the audience want to attend to the next one, we host our dev deep dives every 2 weeks. So the next one would be in 2 weeks from now. Make sure to RSVP so that you get a reminder for when it happens, but it's always Wednesdays at 12:30 p.m. Eastern, alternating with our DevRel lives as well. Just to put that out there, really thankful for you guys joining, and also for anyone watching on Twitter and YouTube. Really appreciate your guys' support, and we will see you next time. Thanks, everyone. Bye bye.